For the most part, as we've been looking at light, we've been focusing on the wave aspect of light. However, recall that I did mention that light also has a particle aspect to it. And as we go forward, we're going to be paying more and more attention to this particle aspect. Now, the name we give to the particle aspect of light is a photon. And so we'll be talking about the photon model of light. So then the very first question you might ask is light a particle or a wave? And the answer is that that's actually not a good question to ask. Everything, by this I mean matter, light, you name it, everything has both a wave nature and a particle nature. This realization came to light in the early 20th century to resolve two problems. One of them is called photoelectric current. We'll treat that later. The other one, which we'll touch on briefly here, is black body radiation, which is the light that something gives off just because it's hot. We've already talked about that a bit in our treatment of mechanics when we were looking at thermodynamics and saw that the three ways that you could transmit heat. Transmit heat was by conduction, convection, and radiation. So anything that has a temperature emits light, and we'll visit that a little more right now. But it turns out to resolve those two things, physicists had to have a major rethink of everything they thought they knew about physics. It turns out that the house of physics was built on a bad foundation. And in the early 20th century, the house of physics got jacked off of its foundations. A new basement was poured, and then the house of physics was set back down on new, much more solid foundations. This is the era of modernity for physics. So we call this modern physics, even though it's well over 100 years old at this point. But it's just the era where we had to have a major rethink of things. This is sort of like, say, modern art, where with the development of the camera, the need to do realistic portrayals decreased, and so artists felt more freedom to express things in other ways. Thus, the era of modernity for art, which is also now well over 100 years old. So anyway, it turns out everything has both a wave nature and a particle nature. So how do we interpret that? The usual way we interpret this is to say that the wave nature dictates the probability of detecting the particle of detecting the particle at a given location. So, for instance, we can go ahead and revisit Young's experiment. So you remember Young's experiment was where we had two closely spaced slits. We had a plane wave of light come into it. When we looked at the screen over here, what we saw, I'm just indicating schematically here, is that there was a bright central peak, and then there were dimmer peaks off to each side. Now, if I were to go and take a look, so now this is looking from this direction, if I could attenuate this beam down super duper weak, and this has been done in the lab, You can attenuate it down to the point where one particle of light, one photon, is approaching the apparatus every second. And what will happen is that you'll just see a photon land somewhere. Now, if you let this go for long enough, what will happen is you'll see an intense buildup of photons landing in the central spot, a less intense buildup at the first maximum, and even less intense buildup at the second maximum. Like so. Now, it turns out that generally, for a typical light source, you have way more than one photon a second coming in. And so what's happening here is just you're getting bathed in it, and it looks like you've got a continuous phenomenon happening. But the deal is that the wave model of light said this is going to be the brightest area. And what happens is this is where the most photons per second of light will land. The wave model of light says photons don't land here, and that says light doesn't land here. Turns out no photons ever land there. Wave model says less intense light here, fewer photons per second there. Now, like I say, for visible light, in a normal situation, unless you're doing something weird in the lab, you are having zillions of photons striking the apparatus every second. And so there's no real way that you could distinguish one photon from another. Basically, the way I like to describe it is that this is like when it's raining in sheets outside. You know, if you've ever seen that, you're well aware that rain comes down one raindrop at a time. But sometimes when it's raining down super duper hard, we'll say that it's raining in sheets. And it's still individual drops of water, but they're coming down so close together, so fast, that you can't tell that you have individual drops of water, and it just looks like sheets of water are coming down from the sky. And so that's the same idea here. Now, it'll turn out that there'll be situations as we get to shorter and shorter wavelengths where this raining in sheets isn't really going to happen anymore. And then you pretty much will be seeing the behavior of one photon at a time, and there it makes much more sense to talk about the particle nature. So let's go ahead and get this done a little more concretely. It has been shown that the energy of a photon, so each photon of light carries a specific amount of energy, it's equal to hf, where h is a number called Planck's constant. This number is now an exact number due to the 2018 redefinition of SI, and it's what's used to define the kilogram. But we'll just use the first few digits here and just say that 6.63 times 10 to the negative 34 joules seconds. So the idea is that every single photon gives us this much energy. So if, say, I have some sort of a transmitter or a receiver for that matter, the amount of power that gets transmitted or received, well, that's going to be the energy over the time. So each, in a particular amount of time, delta t, we'll have had delta n photons land on our detector, and each one of those photons will have an energy hf. And then just as a quick reminder, just like we did for sound, we can define the intensity of light as being the power detected over the area or the power transmitted over the area, whichever way. And so this is the deal. If you have, for a given power, if you have low frequency, which will correspond to long wavelength photons, this is going to be the rain and sheet side. So the wave nature dominates. As we get to high frequencies, which will correspond to short wavelengths, so start thinking X-rays, gamma rays, this kind of thing. Here, each individual photon is so powerful that it can do sizable damage to things like DNA molecules and stuff like that. At that point, you are literally detecting individual photons at a time. And so over here, the particle nature is going to dominate. But make no mistake, we always have both the wave nature and the particle nature present, no matter what. And this is what physicists call wave-particle duality. The analogy I like to make to this is like, say, if you hold up a coin, it would be a bad question to ask, is this object a head or a tail? You'd say, it's a coin. Coins have heads and tails. And so in physics jargon, what we would say is that we have head-tail duality. It's two sides of the same coin. Physicists haven't come up with a name for the quote-unquote coin for which the heads is the waves and the tails is the particles. But it is two aspects of the same thing. And so there's always the wave nature, there's always the particle nature. The wave nature dictates where you'll be most likely to detect a particle. All right, so let's just make this kind of concrete just to show how this might work. And here we'll be working in a region that is very much raining in sheets. So let's say you have an AM radio transmitter that's transmitting at 1 kilowatt, which isn't very much for a commercial station, but for an amateur station, that's not unreasonable. And let's say you are transmitting in the commercial band, so you shouldn't be doing this if you're an amateur, at 900 kilohertz. So this is within the AM radio band. And let's just say, okay, if you're transmitting at 1 kilowatt, how many photons are you emitting per second? So we're going to be asking for the photons per second, delta N over delta T. So we can say, all right, the power is delta N over delta T times, that's a terrible delta T times HF. So I can rearrange delta N over delta T will be equal to the power over HF. Okay, so for our AM radio station, let's say it's 1,000 watts. Planck's constant is 6.63 times 10 to the negative 34 joule seconds. And our frequency is 900 kilohertz, so kilo means times 10 to the third hertz. All right, let's just pay a quick attention to the units here. So hertz is same thing as 1 over seconds. Remember, we write it this way so we can tell it apart from radians per second for angular velocity. So these hertz will cancel that. Now, a watt is a joule times a second. I'm sorry, a joule per second. So the joules will cancel and be left with 1 over seconds. And I'm going to kind of just leave that there for the moment. So anyway, if you grind the numbers through in your calculator, you'll get 1.68 times 10 to the 30. Now, you can write this as seconds to the negative 1, and you'll see people do that in the literature. But more likely than not here, because you're counting something, you tend to write the name of the thing you're counting. So you'll say something like photons per second. It's not wrong to write seconds to the -1, but this is, at least to my way of thinking, probably a better way to communicate what you got. All right. Now let's repeat this for a 1 kilowatt station that would be operating at 90 megahertz. So this is squarely in the FM radio band. Alrighty, so in that case, we can go ahead and just plug back in again here. We already worked out that delta N over delta T was P over HF. So that'll be 1,000 watts over 6.63 times 10 to the negative 34, 10 to the negative 34 joule seconds times now 90, and remember the mega prefix means times 10 to the 6th hertz. All right, that's going to work out to be 1.68 times 10 to the 28 photons per second. So this is a factor of 100 lower than AM. In both cases, I mean, there's no way that any detector is going to be able to pick up whether you are transmitting or receiving 10 to the 30 or 10 versus 10 to the 28 photons per second. That is just a ridiculously high rate at which the photons are coming in. So that's what I mean by it raining in sheets. There's no way you're going to be able to pick out the individual photons with whatever detector you're using. Now, as you go to higher and higher and higher frequencies, by the time you get into the gamma ray side of things, now the beam will be so attenuated that you will be thinking about the individual photons more, just because each individual photon carries a lot more energy. So, lower the frequency, longer the wavelength, the lower the energy photon, the more of them you need to carry the same amount of energy. Higher the frequency, shorter the wavelength, more energy in each photon, the fewer of them you need to carry the same amount of energy. All right. So I also mentioned blackbody radiation. So this, which we saw before when we were taking a look at thermodynamics. So this is the light that gets emitted by anything with a temperature. And we've seen before, so I'm not going to revisit it here, but the Stefan Boltzmann law that we saw before, which says that the rate at which we can radiate heat or absorb heat goes as the emissivity of something, which was a number between 0 and 1. Perfect reflectors are 0 and perfect absorbers are 1, times sigma times the surface area of the object times the fourth power of the absolute temperature, and where sigma is the Stefan Boltzmann constant, which you can remember by going 5, 6, 7, 8. 5.67 times 10 to the negative 8 watts per square meter Kelvin to the 4. It turns out that in order to come up with this relationship, you actually have to take into account the photon model of light. To do it properly. But like I said, we visited this before, so I'm not going to make too big of a deal about it now. The new bit that I'm going to add in, though, is to talk about the spectrum of the light that gets emitted. So go ahead and take a look at this demo here. So what you're seeing here is a camping stove that's currently running at a pretty low temperature. And I want you to take a look at the color of the flame, especially near the metal part. You'll see that it's not a vibrant blue, but has a little bit of red tones into it. Now, as we crank this up, the flame will get hotter. And you'll see that the blues are now more pronounced, and we've lost most of the red tones. So what you're seeing here is that when something is colder, the light that it emits is redder, and when something's hotter, the light it emits is bluer. So anyway, there is a relationship for what the peak wavelength of the light looks like. And this is given by Wien's displacement law. Yeah, I know you think you'd be Wien, but it's German, and the way you would pronounce that is Wien, where this is a V sound, and the IE would be pronounced as a long E. So Wien's displacement law. And again, the derivation of this comes from understanding that light has a photon nature to it. Says that the peak wavelength in the emission spectrum can be given by 2.9 times 10 to the 6 nanometers Kelvin over the absolute temperature of the thing. Now, what will happen is the light will get emitted at every wavelength. So if you've got, say, something relatively cold, like the intensity is going to look something like that as a function of wavelength. And these will be long wavelengths here, so this is something cold. The hotter you get, so hotter, so something hotter will give a spectrum more like this. And there is a tail all the way up as high as you'd like, but it's vanishingly small. But the deal here is that the central peak has shifted to shorter wavelengths. So this is lambda max for something cold. This is lambda max for something kind of warm. And then when we get really hot, like the flames you were looking at, let's try that again. Something like that. That would be lambda max for something hot. So the hotter you are, the bluer you are. And so what you were seeing happen in the demo was, okay, it was always pretty hot, but as I cranked up the temperature, you lost some of the reds because the whole spectrum, because the whole distribution shifted over. You emphasized more blues and less reds, so that's why the change in the shade of blue that you saw. All right, let's take a look at this numerically, just to get some sense of this, and also to show you how astronomers know what the temperature of the photosphere of a star is. So let's find the peak wavelength for the sun. Now it turns out that the temperature is 5,800 Kelvin, and the way the astronomers get this is by measuring the spectrum and using Wien's displacement law, but we'll do it the other way. So I'm plugging in. This will be 2.9 times 10 to the 6th nanometers Kelvin over the temperature. So this will be 2.9 times 10 to the 6th nanometers Kelvin over 5,800 Kelvin. This will give us a wavelength of 500 nanometers. And if you look in any spectrum table, you'll see that that is green. Yep, that's right. The sun is green. Now, your first question is going to be, gee, it sure looks yellow. Why is that? And the reason it looks yellow is twofold. Part of it is it turns out if we go ahead and plot the intensity of light as a function of wavelength for the sun, long tail. There we go, something like that. It turns out that it peaks pretty much, the peak wavelength is pretty much right in the center of what our eyes can detect as visible light. So shorter wavelengths are on the blue side, and longer wavelengths, remember, are on the red side, and you peak in green in the case of the sun. But it turns out that I didn't really, here, let me try drawing this curve one more time. I tried. So I'm trying to show without a lot of success. So that while it comes, there's basically more reds hanging out over here than there are blues. And this winds up shifting things around. So even though the peak is in the green, both the fact that there's more reds and less blues, and also just plain how the cones in our eyes work, we perceive that mixture as yellow. But the brightest part of that mixture is indeed green. So if you want to annoy somebody, you can keep talking about how the sun is green, and you will be technically correct. Let's just go ahead and repeat this for Sirius A. Which is a star in Canis Major. This is the dog star, and actually gives rise to the name the dog days of August, because Sirius A and the sun are actually roughly in the same part of the sky in the month of August. And it turns out that Sirius is one of the hottest stars that you can see with the unaided eye, at 9,940 Kelvin. So the idea, even from ancient time, was somehow Sirius was making things extra hot. Now, the thing is, Sirius is so far away, it doesn't. The reason why it's hotter in August in the northern hemisphere has to do with the fact that the Earth is tilted. But I digress. Anyway, if we go ahead and repeat this, what we get is, so our peak wavelength here, just plugging back in again, 2.9 times 10 to the 6 nanometers Kelvin over 9940 Kelvin will give us 290 nanometers, which is firmly in the UV, but Sirius looks blue. So what's up with that? So again, it's the same deal, and this time, having learned my lesson, I am going to draw my red and blue boundaries first, red and violet boundaries first. There we go. So if I plot intensity as a function of wavelength for Sirius, it turns out that it comes to a peak way over there before it falls off. So this over out in the ultraviolet. But now you can see what the deal is. We have more blues and less reds in the part that we can actually see. So when you look at Sirius in the night sky, you see that the star is blue. We can go ahead and repeat this again one more time. Let's do this for Betelgeuse. Delgeuse. This is in the constellation Orion, the Hunter. Betelgeuse is 3500 Kelvin. So the peak wavelength for Betelgeuse will be 2.9 times 10 to the 6th nanometers Kelvin over 3500 Kelvin, which is 830 nanometers. And this turns out to be a peak in the infrared. So, intensity, wavelength, once again, having learned my lesson, we'll draw the red, we'll draw the blue. So if we go ahead and draw the spectrum for Betelgeuse, it's actually not too far off. It's quicker fall off though. There we go. You can see the reds dominate over the blues, so you look at it and you see primarily red, but most of the emission is happening in the infrared. This, by the way, is why it is that many governments around the world have banned the use of incandescent light bulbs in all but specialty uses. It turns out that your typical incandescent light bulb that was used for household lighting was even colder than the star Betelgeuse. That means that you peaked even more in the infrared and even less of the light was emitted in the visible. It depended exactly what the wattage of the bulb was, but rough numbers, about 15% of the light was emitted in the visible and almost all of the rest of it in the infrared. What this means is that an incandescent light bulb, quite frankly, was a better heater than it was a light bulb. Okay, your toaster is even better than that. If you look at a toaster, you'll see that the coils are glow a dull red. They're really super duper bright in the infrared. But again, our eyes can only see the bit that tails through in the visible. So in fact, the toy, the Easy Bake Oven, for a very long time, what provided the heat to allow you to cook those teeny tiny little cakes was just a light bulb. And that's because it did a better job heating an Easy Bake Oven than it did making light. Now, from an energy conservation point of view, there are an awful lot of artificial lights out there. And so by replacing incandescent lights with either compact fluorescence or now more commonly LED bulbs, which emit almost all of their light in the visible, even allowing for some losses. You're getting something like 5 times more light in the visible for the same power, or usually, since what you care about is how much light you're getting, means that you can use something like a fifth of the power. That's a huge difference given how much of electric use is providing lighting. And that's why you can see, there are electric utilities out there that have names like thus and such water and light, because lighting is just that big of a deal in the usage. So that's why that's why things have changed, and we're only able to get incandescent light bulbs for specific specialty uses and not for normal household lighting. Alrighty, so with that ends our treatment of light for now. The photon stuff will be coming back as occasionally as we visit modern physics. So we'll catch you later.